Okay, let's start again. I do not have any fancy introduction today. I mean, I liked when it started by saying how great I am. And, okay. Okay, it's a cold start. Okay, let me remind you what we said today, and I will finish lecture 1 today. So I feel like Chris, right? He was always finishing lecture 1 during the second one. We look at the following problem. You had a random variable x star that came from a known probability distribution P of x, which we call the prior, and it was sent through a noisy channel, or if you want, it was measured. And what you measured actually was something that was given by square root of lambda x star plus z, where z was taken from a too much coffee. A normal distribution with zero mean and unit variance. Okay? Then I try to tell you, I heard that some of the best thing that you should do is to consider the posterior distribution. So knowing why, you can write the posterior distribution on the unknown variable. Okay? And this is something we called P of x given y. And this is your probability, somehow your belief of what is the variable x, given you have observed the measurement y. Okay, and if you remember, it was written exponential minus plus x y square root of lambda divided by a normalization, which depends on y. Okay? Now, this is a probability distribution of x. Okay? So that gives you a probability that x was 5, or x was 2, or x was minus 1, or something. Okay? Now, you might want to say, fine, but I want to give one number. And I heard that if you want to give one number, what you should do is to take the average of this distribution. Okay? So I actually say that, you know, we might as well consider this as a Gibbs distribution over x. So if you want, this means okay. And I argue that this is a good estimator of the unknown variable x star. Right? The mean of the posterior distribution is a good estimator in the sense that it is actually the one that minimizes the mean square error on average. That's a good thing to do. Okay, so that was the first thing I said. Point B, this is what you should do if somehow what you are trying to estimate. Now, if you are not trying to estimate, but you are a statistician, and you want to know, in general, what is the best estimate you get, what is the error you get, right? So if you are the statistician, you know the problem was made, and you are doing an analysis. In particular, if you are the one doing the experiment, you know what x star is, and you know what z is. Okay? So you might as well rewrite this distribution like this. So we just replace y by its value. All right, so lambda x star plus x square root of lambda z okay, so this is completely equivalent, of course, because y is exactly given by this. But okay, sometime we're going to use this one. A third thing that I said is that a nice quantity to compute, if you want, if you're a statistician and you want to know what kind of error you might expect in this problem, in the mean square error. So this is the average over z and x star of x minus x star squared. And I told you that this was equal to Q0 minus m, when Q0 was the expectation of x star squared, and m or the average scalar product between your estimate and the truth.
Sorry.
Yes?
What's Z in the first equation or the second one?
It's a random noise.
Below.
This one, it's a normalization.
And the other one is the...
This one is this guy.
Okay.
Right? So here I had y, but I might as well replace, I mean, if I am the statistician and doing the analysis, I might as well replace y by square root of lambda x star plus z. Okay? Okay, and that's it. Oh yes, and then I also derive this great set of relations, which I call the Nishimori relation, and I will rewrite them here for you. So the average over y of any function of x. Okay, if you take a function that depends on two independent copies of the system, take Gibbs average, the average over disorder. I told you this is exactly the same as the average of the same function with one copy of the system, and you replace the second copy by x star, the hidden truth. Okay? So that looks kind of magical, but this is just saying one thing. X star, okay, the truth is just distributed in the same way as any x in your posterior distribution. Okay? So that means the following. If you want to know someone, you have this posterior distribution and someone asks you, oh, give me a x taken at random from here. Well, you don't have even to think. You just, okay, let me give you x star. I know x star is taken from there. Okay? So if you want, x star is an equilibrium configuration. And this is what makes this problem a bit different from standard stat mech. Okay, so this is what I said yesterday. And now let me finish what I really wanted to say yesterday. So there is pretty much not much that we can add to this problem. I mean, this is, after all, a single variable with noise, so there's not much you can write. So I will just give you two results. Okay, the first one is assume, just to show how it looks, assume that p of x is just a binary variable, plus or minus 1 with probability 1/2. Okay? In that case, you can compute m. You can actually write explicitly what this is. I mean, it's not so hard. This is how it looks. So I will let you check this. Parabolic tangent of lambda plus square root of lambda u. Okay? And so if you want to know what is the mean square, the best mean square error you should expect as a function of the signal-to-noise ratio. Okay, and Q0, of course, is 1. I mean, this is the expectation of the square of this variable. The square of this variable is always 1. Okay, so the MMSE is just 1 minus m. This is a one-dimensional integral. You can do it, put it in a computer. For people who have done spin glass, that should look familiar, by the way. And it looks, wait a sec. It starts from 1, and it decays slowly like this. Okay. Yes? Sorry? Y? No. It's lambda. There are no y here, right? This is the total average over everything. So it must be a number. Right? The minimal mean square error is average over y and over every, okay, so MMSE is the average over y. All right, it's here. Okay, so averaging over this is the same as averaging over y. And Sorry.
Yeah, that one. I just cannot read it.
All right, let me write it for you like this.
Okay.
Okay? Now, this is a great moment because I can introduce this notation. When physicists write a big du, what they mean is a small du with a Gaussian distribution. Okay? But since we have this Gaussian distribution everywhere, we shorten that kind of notation to us. And it's a standard thing to do. All right, so this is interesting. I mean, not so interesting because, after all, it's one single variable. But somehow this is telling, you are giving me lambda, so the intensity of the signal-to-noise ratio in this problem, let's say 2. Okay, I look this curve, and let's say, I don't know, this is 0.2. And I know that I should expect, on average, to have an error 0.2 when I'm using the posterior mean. And 2, I know that there is no way I could beat this on average, because this is the best estimator if you want to have a good mean square error. Okay? So that's the kind of thing you can get from this analysis. All right, so it's kind of boring because there is one variable, okay, of a single spin if you want, so no phase transition, no cooperative phenomena, no diverging whatever, so it's not very fun. Okay, no threshold, no phase transitions. So we are going to move to something more interesting. But before, if you are courageous, yes, Francesco? Yes. Yes. But yeah, then I use the Nishimori relation, and Q is equal to M. So I had Q0 plus Q minus 2M, and Q is equal to M, so we had Q0 minus M. Okay? Fair enough. Now, for those of you who want to have fun, oh yeah, first of all, I need something. I need to write something, and I need to keep it until the end. All right, so I will write it. I will write it here. Okay, so even if it is a single variable, it's kind of good to write the free energy. That is, there is a log of minus log of z. Okay. And since we are in some kind of disordered conference, I might as well write the average free energy. That means the average of log of z, okay, of minus log of z. So by the way, the mathematicians working in this field now, they are defining the free energy as log z. And it's real mess, and we are telling them, no, there is a minus, and they don't understand why we insist on the minus. And it's not us, it's Clausius. So anyway, so if you see somewhere of free energy being equal to log z, well, it's one of these crazy guys. Anyway, let's write it. So the free energy, on average, should be minus. You remember in this problem, beta is 1. Okay, so there is no kBt in front. So I should average over y, or if you want, over x star and z, log of z. Okay? So we can write it explicitly in this case. Right? So this is our probability distribution. So let's write this average. Right, so first we have dx star p of x star. Then you have this Gaussian average. dz, well, now that you are familiar with this notation, I might as well do it this way. Then we have a log. And now we have an integral over dx of this thing here. All right, so this is the average free energy of our problem. And now I know what you are thinking. You are thinking, well, there are 3 integrals. That must be hard. And no, it's not hard. I mean, come on. It's just 3 integrals. First of all, you can put this in a computer. Secondly, I mean, this is a quadratic form in X. So for many forms of prior, you can actually compute this. For instance, if your prior is just plus or minus 1 with probability 1/2, you can actually compute this integral. It gives you a cosh. If this is a Gaussian, you can also compute it. If this is a mixture of Gaussian, you can compute it. If it is a flat distribution, uniform distribution between A and B, you can also compute this integral. It gives you some R function. And I mean, in many cases, you can come back to 2, and actually in many cases, you can come back to only one single integral. So it's not so bad. And in the worst case, free integral, I mean, piece of cake, right? I mean, the computer can do this. So let's say that this is a number. Now, I will need this expression later on. So let me call this lambda 1, this one lambda 1, and this one lambda 2. Okay? And I will call the function phi den of lambda 1 and lambda 2 exactly this expression. Okay? I'm just doing this because I will need this expression later. And of course, the free energy in our case is just phi den with lambda and lambda. It's the same. Okay? But later on, I will need this, so I want to define it now. All right, no question? I mean, this is just... All right, and for those who want to have fun... Yeah, good point. No, you're right. So this is lambda 1. This is lambda 1. And the lambda 2 is the one that is the X star. Okay? It's absolutely unimportant so far, because all of these are equal to lambda. But, OK, I will use this expression later on.
The first lambda 1 shouldn't be lambda instead of lambda squared?
No, it's a lambda square up there. So I don't know. Yeah, you might be right. Let's see. Yeah. Yeah, you are saying this one is a lambda. Yeah, you probably are right. I was so happy with the squared in front of the X. Yes. Right? Did I wrote a lambda yesterday? Well, that probably I was correct yesterday because I was worked up. OK, sorry about that. All right, so anyway, an exercise for those who want to have fun. You remember that DM-Semerjian defined to use a mutual information between two variables. OK, so you can try to show that the mutual information between X and Y is exactly equal to this free energy, and there is a trivial correction, plus lambda expectation of X star divided by 2. Okay, so it's the first exercise. It's very easy, but it's good to do. It's actually, I think, in the overleaf file. And a second exercise, which is more fun, compute the derivative of the mutual information with respect to lambda, and show that it is equal to 1/2 of the minimal mean square error. Okay, that looks magical, but it's not. I mean, I'm kind of telling to you, look, the mutual information is like the free energy. The derivative of the free energy with respect to lambda, it feels like deriving, the derivative of the free energy with respect to beta. And we know that when you derive the free energy with respect to beta, we have things like the energy. Okay? Or in that case, yeah. Right? So this is exactly the same kind of relation, thermodynamic relation, that we are used to in statistical physics. But people in information theory were very surprised by such result. Actually, this is called the IMMSE theorem. And it was proven in 2005, I think, by Shamai, Verdoux, and Guo.
Can you remind us what is MMSE?
MMSE is the minimal mean square error. That is this thing. OK? So that's really as a taste of, you know, you derive the free energy by T and you get the entropy or that kind of stuff. I mean, it's really the same kind of thing. And there are a lot of relations like this in information theory. They call them area theorems, and we know that they are just thermodynamic integration things. Yes?
Also, I mean, maybe it's because I came in late, but can you remind us of part B, the statement B?
Oh, yes.
You eliminated, somehow you eliminated.
So if you are doing the if I'm giving you y, what you should do is to sample from this distribution. Okay? Now, if you want to analyze what is going on, you are the one doing the experiment. So you know that y is equal to lambda, square root lambda x star plus z. So you might as well replace y by its value and average, instead of averaging over y, you can average over the distribution of those two. That's all I'm saying. Okay? And if I want to do some analysis, I need to know what x0, x star is, right? Because otherwise, how do I know how close I am?
Oh, I see. X star is a specific.
Is the truth. It's the one I use to generate the y and give you, right? I mean,
While X is like a free variable.
yes. X is kind of my belief on what x star is. Right? Ideally, I would really love if P of x given y is really peaked around x star, which will be the case when lambda is very large, of course. In fact, you can see that this is almost a Gaussian, and the mean is, well, if you go here and you look at it in a quadratic form, you will see that it's a Gaussian. Lambda will play the role of the inverse variance. So when lambda is large, this distribution will be extremely peaked on x star. Okay, so you will have a good guess. When lambda is small, well, of course you have something harder. Okay, so you see there was a lot to learn anyway, even with one single variable. Okay, but it was not statistical physics because we need cooperative phenomena. Okay, that's end of lecture 1, and now we try to move to something more interesting. It's more interesting from the point of view of statistical estimation, but also from the point of view of statistical physics. And I will try to convince you why. So we move to, right, we don't need this so far. All right, we move to lecture 2. And it's called spike matrix models. All right, that looks really scary, and that doesn't sound like anything we know, but wait a minute. Okay, so we are still interested by some kind of denoising problem, but we will be trying to do something more interesting. And so this is what I will be doing. Now, I have a x star, but it's a vector. Okay? So there is an unknown vector of variable, x1 star, xn star, okay? And each of those guys is coming from the prior distribution P of x of xi. Right? So it's very similar to what we had before, except now I'm creating a full vector of variable. Right? I want to know this vector. Okay, of course, what we could do is to say, fine, let's imagine I'm looking to lambda times this plus random noise, but then it's exactly the same problem as before, so it's not so fun, right? Because in that case, every single element of the vector has a Gaussian noise, and everything decoupled is the same problem. So let's try to look at something more fun. Okay, so what we are going to do is the following. We observe the matrix Y, which is n times m, which is equal to square root of lambda over n times x transpose plus w. Okay? Now this is also a matrix n times n. Okay, so this is a vector which is like this times a vector like this. So this is a matrix. Actually, this is a rank 1 matrix. So that makes sense. And if you are confused, let's look what this is element by element. Okay, I'm writing that yij is equal to square root of lambda over n. Okay, I forgot the stars here, xi star, xj star, plus wij. And this matrix here is symmetric, by the way. Okay, so each element here is taken from pi, from px of xi, and the wrj are, like before, taken from a Gaussian with zero mean and unit variance. But I have to make sure that yij is equal to yji. Okay, it's a symmetric thing. So, if you want, this is what I'm doing. I have my vector. I'm creating a rank 1 matrix with this vector. I mean, so I'm multiplying by his transpose. So now I have an n times n matrix with a lot of redundancy. Okay, you can think actually it's a way of doing a code. It will be a terrible code, by the way. I'm telling you already. But you can think about it this way. And then you send it through this noisy Gaussian channel. And what you measure is a matrix where this element plus random noise. Okay, why is it called a spiked? So there is a model here because there are a lot of variation over this. I will not have time to discuss them, but okay. So why is it called spikes? Because if this guy is not here at lambda 0, this is just a random IID Gaussian matrix, right? The Wigner matrix. So what I have done is just to add a perturbation to this matrix. And in fact, if you think about it, in terms of spectrum, what I have done is to change one single eigenvalue of the spectrum. So it's really a spike, if you want, and this is why people like to call this model spike matrix models. Okay. Yeah, I will say that in a while. So why is it interesting? It's interesting in the context of statistical estimation because, well, this looks a bit like what you have when you have some matrix with data polluted by noise. Okay. In fact, one of the first things you do when you have a matrix, like the correlation matrix, is to do what is called the SVD decomposition. And then you keep only the first leading eigenvectors, and this is called the PCA, principal component analysis. Because somehow what you think is that, well, I have one, the leading eigenvector has information and the rest is noise. Okay, so this is the kind of model of this. Imagine you really have a matrix in which most of, a lot of things is noise, and you have a bit of information. Question 1, can you recover the information? Is it possible to get a good estimate of this vector? Question 2, is it possible in practice? And by this, I mean, is there a good algorithm to do? Okay? And we know there is a good algorithm, actually, in many cases. It's just to do a eigen decomposition and to look at the spectrum of this matrix. Okay? But I will come to this later. All right, so there are certainly good reasons to look at this for machine learning or statistics. Let me give you a variation on this problem. Imagine instead of looking to a spike matrix model, I look instead of a model like this. Y, I, J, K equals square root of lambda, xi star, xj star, xk star, plus wij, and now I need to be careful with the division here. N is 3 minus half divided by 2. All right, the square root of n is here because this is the scaling in which things are interesting, and you will see this later on. So what I have done here. Exactly, this is a spike tensor model. Okay, so w here has 3 indices, so it's really a random tensor. And I'm adding a spike to the tensor. I'm giving you the tensor, and I'm telling you, okay, so is there any information in this? So that will be a problem of matrix decomposition. This is a problem of tensor decomposition, which, by the way, is really, really, really hard. Okay, it's hard because there is no such thing as eigenvalue decomposition for tensors, which is really a pain because tensors are cool, but that's life. Yes?
So how can we interpret n?
N is the size here. Okay? So the point is the following. Here there are really a lot of information. because I have n squared number, and I have only n unknown. So if I want to make this model interesting, I need somehow to divide to have the spike to be small. Otherwise, it's really too easy. And one way to see this immediately is to look at the spectrum of y. And if you do experiment, well, you will see that if you don't divide this by n, the spectrum always looks like this. So it's easy. You take the, just take the eigenvector associated with this guy, and you're in. Now, if you put n here, then depending on the value of lambda, you will either be in this situation or in this one, in which you don't see anything. Okay? So this is telling two things. One, that this is a correct scaling, and two, that this is a good algorithm already, right? I mean, this is actually true in general. I mean, if you have a matrix and you want to know something about the matrix, we know that looking at the spectrum is a good thing to do. Okay, so here now, there is this mysterious 3 minus half over 2, which is a bit harder to argue. But if you wait 1 minute, you will see why this is actually the correct scaling. Okay, so what I want to do today is to give you the solution of this problem. That is, compute the free energy, compute the best MMSE we can get. So you give me lambda, you tell me what is the distribution of x, and I can tell you what is the best error you can ever achieve, whatever you tried, on the construction of x. Okay, and to do this, we will just follow what we have done yesterday. And I'm on time. But before this, okay, because, I look at you and I see a lot of people are getting nervous, and this is it's very interesting, but I'm a physicist. Okay, so let me go back to physics.
Can I ask before you do that?
Yes.
Is the best error, how is it related? How is it formulated in terms of mutual information?
Good point. The best error is the derivative of the mutual information with respect to lambda. So think about the mutual information here somehow as some kind of free energy, right? And the best error is some kind of energy. So I get 1 by deriving the other one.
But non-minimization, not that equal to 0? Or?
Well, okay, so I'm not, remember that DM had the mutual information, but what he was doing was to try to play with the prior, right? When you are doing coding theory, you try to think, okay, what kind of variable I should send into my channel such that I can send information? I do not have this choice. Someone told me that this is what I did. So for me, this is just a function of lambda. It's a number. Now, of course, if you want to think in terms of variational physics,
I may tell them to send it.
Yeah, but that is true if you are doing communication. But this is not communication. This is really a measurement. There is x, and you are given some noisy version, and it has the prior it has. Right? So the vocabulary is the same, but the goal is different. That's
Okay.
yes?
How did you manage to go from 2 indices to 3? And why does it have more information than it had before?
I don't think I did. I don't think I said this. I'm just saying that this is one problem, and this is another problem in which there is a tensor y, and I'm trying to decompose it into a product of 3 vectors. These are just 2 different problems.
Okay, what's the benefit of doing it 3 times as opposed to 2?
Just a different problem. I know. Someone is giving you, look, I have these tensors, and I know it's a rank 1, order 3 rank 1 tensors. Can you decompose it? Can certainly happen. In fact, a lot of time, data are tensors. Right? I mean, for instance, if you have information about 3 objects, you have a table with 3 different coordinates, right? So you don't always work with matrices. Sometimes you have tensors. Yes?
Maybe you answered both questions and also make the differences. But again, you give an example of the concrete problem where was in this setting.
Yes, I could, but I won't. Okay? Because I will actually show you something better. Right? But okay, if you want one problem, like, okay, let me give you a problem. Fine. I will do both at the same time. That's fine? All right, let's take a particular case of this problem, and this problem. For instance, when x is equal to plus or minus 1. Okay? Now, that means that my vector is looking like this. Okay, let's assume someone was nice enough to order it. Of course, it never looks like this, right? It should be like a plus 1, minus 1, minus 1, plus 1, minus 1, something like this. All right, how does x star looks? Well, it's a matrix. Now, on this side, I have all plus 1 times plus 1, so this is basically something which is plus 1 everywhere. The same here. And these are minus 1s. Okay? Now, okay, and of course you can divide by square root of n and square root of lambda, so if you want this. Now I'm adding a little bit of noise to this matrix, so now it will look like this. Of course, if you look at this, you think, well, come on, it's not so hard. I know that the vector was plus everywhere here and minus everywhere here. Yes, but remember, I cheated here because I give you something that was ordered. Now think about a random permutation of this, and it starts to certainly look, not so easy. I will show you actually how it looks when I will have a PDF. Okay. For instance, now let's look at a slightly different case. Imagine if instead of having a matrix here, which is just adding some random noise, I will just randomly flip that kind of thing. Right? We are physicists, come on. Flipping things is the same as a random noise. We can prove this, but I don't want to go into this. Now, what kind of model is this? If I'm giving you this matrix, and sometimes I flip things, or sometimes I erase. Yeah, you already saw it. Yes, this is true. This is a binary symmetric channel. But I was not thinking of Guillaume's lecture. I was thinking of Chris' lecture. So, I have a vector which is plus 1 or minus 1. So I have two groups. And now I have a matrix. And whenever two guys are in the same group, I have a 1. They are in different group, I have a minus 1. Exactly. That's some kind of community detection problem. Now, the community detection will be this case where I will keep the 1s. Whenever I have minus 1, I have zeros. And then I flip randomly a bit things, because otherwise it's too easy. Okay? So this is something you can map to community detection. And this is actually a version of the dense stochastic block model. Okay? So I'm not making up this problem. They are very popular these days, by the way, this problem. Okay, so I will show you how this matrix looks. It's kind of fun to look at it and think, wow, there is information in there? And the answer is yes. Okay, so let's keep this x plus or minus 1. And now I will try to show you that not only this is a community detection problem, but this is even something that we spoke even more about. All right, so if x is plus, okay, so first of all, let's write the posterior distribution over x given y. Yeah, if you write, you can write it as a rank-free problem if you want, but then in that case, it's not the stochastic block model; it's something else. And okay, I mean, you can do many variations of problem by adding indices. That's a good thing about computer science. You can make up problems, right? I don't have to say, oh, this is the Hamiltonian of the SEO2 that describes glasses. Okay, I can just wave my hand and say, This is a tradition among mathematicians to look at such problems. And this is true, so that's good. All right. So how does it look? P of x given y. All right, so that's not so hard. It's proportional to the prior probability of x, and then the probability of observing y, which is actually simple. Squared over 2. Yeah, let me forget about any normalization. I will reabsorb it. Okay. In fact, I can even develop the squared. The y squared is not very interesting. This is a probability over x after all, so I will put it also in the normalization like I did yesterday. And so we get p of I, px of xi, all right. So it will look a bit like the one this morning. So first we have this. Sorry, this is not starred. Xi squared, xg squared, plus yij xi xj square root of lambda n. Okay. Okay. So it's not so different from before, except now I have many spins and they are interacting, or many variables and they are interacting. So of course, computing the partition sum is much harder, but otherwise it looks like before.
Is y necessarily symmetric in these sorts of problems?
Good question. No. You can also look at a version in which you have two vectors and you observe u v transpose plus w, which is not symmetric. And this is actually even more interesting. This is something that can map to clusterings problem, to the so-called mixture of Gaussians, and you can make the same kind of analysis. And the same for tensors. You can look at a tensor made by UVZ and so on and so forth. Right, but we have a finite time. Yes, Marilou. If you think I'm missing a 2 here, and you are right. Thank you. But this time the lambda is not squared. Oh, I'm making a lot of mistakes, but never the same twice. It's good. Okay. Now let's specialize to this case, which is plus or minus 1. Well, if x is plus or minus 1, what is this? 1. So I might as well absorb it into the normalization. Okay? So let's look at this case. And I will do a lot of hocus pocus, and then you will see we arrive at something interesting. So xi is plus or minus 1, probability 1/2. Okay, so p of x given y. Well, I might as well remove this prior, because it's just telling me that x is plus or minus 1. So, okay, if I have to integrate, I can just replace by a sum, but it doesn't play much role. Okay. Now this guy, I can reabsorb it in the normalization, so I don't need it. Okay, so start. This is how it looks. Y, ij, xi, xj, divided by square root of n, and we have a square root of lambda here. That doesn't look so bad, right? All right. How does this look, actually, if this is a plus or minus 1 variable? Sorry?
Ising model.
It's an Ising model with disorder interaction. it's actually the SK model. Or is it? Not quite. SK will be with Yij totally IID random. Okay, but Yij here is not really random. I mean, it is random, but it's not IID Gaussian. It's Wij, which is IID Gaussian. But we had plus square root of lambda over n. We had the spike, right? All right, let's write it this way. So first of all, imagine that we don't know which lambda was used in the creation. Okay, so in that case, I will call this guy lambda star. And I just know that it was created by a spike. I don't know the intensity of the spike, okay? So, square root of lambda. And now here we have Wij, okay, there was a square root of n, so divided by square root of n, plus xi star xj star divided by n, square root of lambda star, xi xj.
Then what is lambda here?
What is?
Lambda without a star? Yeah.
Somehow it's your belief of what lambda was. Okay? I mean, if you don't know which one I used, you use any one. Of course, if I'm telling you, hey, I created thing with lambda star, well, you will choose the same. Okay? And in fact, I will always choose the same, but I want to do this for a good reason that will appear in a few minutes. For the same reason, I'm using lambda 1, lambda 2 here. Yes?
So should we include some distribution over
X?
lambdas?
Yeah, if you want to guess what lambda is, you can be Bayesian over lambda. I'm not doing this. Okay. Let's say it's really formal that I distinguish between the two. Of course, let's assume that we know it, but because of... Okay, now I'm using a very powerful identity. I will say that xi star squared equal 1. Okay? Now I can insert this inside. Right, I will insert it here. So xi star wij xj star plus 1 divided by n square root of lambda star xi star xj star. Okay, I'm almost there. Now I will define Si equal xi star. Now what is the distribution of this? You know, if it is an IID Gaussian and I multiply it by plus or minus 1, well, I mean, it's still an IID Gaussian. It doesn't change too much. Okay? So with this, what I'm doing actually is coming back to this problem. Si, Sj, Gij. And now what is Gij? Gij is a random Gaussian plus a number. Okay, so I have created actually a spin glass. It's really a Shannon-Kirkpatrick model, except that I have a non-zero mean for my coupling. And that's the only difference. So this matrix spike model is just the Shannon-Kirkpatrick in disguised, except Gij is sampled from a normal distribution with mean. I probably forgot the square root of n here. With mean square root of lambda star divided by n, and variance 1 over square root of n. Sorry? Variance is 1 over n. Thank you, Federico. So all the things that I've told you about this model, if you don't like it, it's fine. What we are doing is just studying the Shannon-Kirkpatrick problem except JJ is not with zero mean. Right? Now you see that there is, when I was not lying when I said that these problems that you see in estimation are really very, very close to what we do. And now, what happens if I do the same thing with the tensor spike model? What do I get? I get the p-spin model, right? So the p-spin model, we know it's a good model if you take it randomly with zero mean for glasses. Well, at least for mean field glasses. And the rest is another question. And if you add a non-zero mean, well, it's a good model for that kind of tensor decomposition. The same trick can be done as well for the spherical model. Okay, so let me finish my mapping here. What should be square root of lambda in general for this to look like a stat phys problem? It's beta. And the square root of lambda star, well, this is the mean of the distribution, so let's call it J0. This is how it's called, actually, in the Sherrington-Kirkpatrick problem paper. No, I mean, even before, actually, I think it was, or maybe not, but at least this is how it was called by Sherrington and Kirkpatrick when they devised this problem. Okay? If you look at the original paper in the 80s, they were actually looking at this problem with non-zero mean. They were doing machine learning without knowing it. It's cool. It's random. Right? What I have shown you is that if you kind of change variable, this thing which is random matrix plus a spike is just random matrix plus a number. At least for plus or minus one variable.
Sorry, but the way you wrote it, I don't quite understand. That's a number.
Okay, JJ is a number. Okay, but the it's okay. These are the couplings. There are many of them. And I'm claiming that...
That's the JJ.
Yes.
JJ is that whole thing.
Yes. And I'm claiming that there are many of them, and they are distributed according to normal distribution with mean square root of lambda star over n and variance 1 over n.
I see.
Okay? So that means the following. Okay. Well, I might as well do it. If you look at the SK model or the p-spin model with a non-zero mean in the coupling and a temperature, which is 1 over beta and is 1 over square root of lambda, my notation. So everything you have heard so far was about this line. Okay, this is where we discussed everything so far. I mean, we had the lecture by Giulio, and Gilles also mentioned this. This is where we do this glass analysis. Okay. So this exact inference process is done instead here on this line in which you have lambda equal to lambda star. And in the statistical physics community, it's called, for historical reason, as the Nishimori line. Okay, it's because of this is the line where we have the Nishimori relation. Yes?
I also missed, why did you ignore the quadratic term in there?
This is a special case where x is plus or minus 1. So this quadratic term is just 1, I reabsorb it in the magnetization. Yeah, I mean, it's not always like this, but this is interesting because it allows me to go back to what my friends have done. Okay? Yes?
I'm confused by the statement lambda equals lambda star.
Yes. Why? This is a statement, not a question. You are confused. I'm really sorry. What can I do?
What's lambda and what's lambda? Lambda star is true lambda.
Yes.
Lambda is a gap.
If you are doing statistical physics, there is nothing that prevents you from saying, I will study this model with lambda here and lambda star here, which are different. This is a perfectly well-defined model. I have a temperature, which is what it is, and I have a non-zero mean in my coupling, which is what it is. Now, I'm just saying, in particular, if you choose very well these two, in fact, if they are equal, you can map this problem into an exact statistical estimation thing. I agree it's confusing, because if you look at it this way, it has nothing to do with estimation. It's just, well, I mean, I have a temperature, I have a non-zero mean. There is just a line in this diagram with mean of the coupling and temperature, which happens after some work to correspond to a problem of estimation. Okay? In fact, since my spins are not xi star, finding something correlated with the truth means that the S are actually close to 1. So, in this model, if you want to know you have something good, you just look at the magnetization, right? If the average of S is larger than 1, then you have something good. So what we should do is to look at, if you want to solve this problem, and you don't need me, you can look at the old paper in the 80s. You look at the diagram, they are there. And at some point, you are in the paramagnetic phase. So if you're in the paramagnetic phase, the average of S is close to 0. Well, good luck. And at some point, here you go into a ferromagnetic phase. That means that S is close to 1, and you have a good reconstruction. Okay? You want to know? All right. So for SK, how does it look? It looks like this. 1, 1. Right? So there is a paramagnetic phase here. So here the magnetization is 0. And in our language, it means you cannot do anything. Right? It means on average, your overlap, your M, if you want. Now you see why I call this thing M, because after the transformation, it's really a magnetization. Right? So on average, it's 0. So the MMSE is 1, right? Which is what you get by a random guess. Now this is a spinless phase. It's a full RSB phase. I will not go into replica symmetry breaking today. And that's a great thing. You will see that I don't need replica symmetry breaking, which is good. And here you have the ferromagnetic phase. That means M is positive. Okay? And here you have a mixed phase, which is a phase which is both spin glass, so it's glassy, but it has a positive magnetization. So this is how it looks. Yes? I think it is if you in the plus or minus 1, no, but not in the Gaussian one. Right? I think you are thinking of here the fraction of non-zero variable. Yeah, maybe it is. Maybe it is. Okay. Yeah. All right. Never doubt a Roman when you speak about spin glasses. I mean, they know everything. Okay. So, good point. So what happened here? All right, I was not planning of doing this, but I will do it now. What happened here? Magnetization is 0. So that means that if you are using lambda, which is too small, lower than 1, there is no way you can make a good reconstruction. Well, that's life. What happens here? Well, you see that at this point, you enter the ferromagnetic phase. So it means you have something good. Okay, so let's plot lambda here. And here we put equilibrium magnetization. And it has a transition like this. Along the line. Right? You can read off the physics of the machine learning problem or the estimation problem if you want along the line. So in this case, there is a second order transition. And if you are running a Monte Carlo algorithm, you can actually compute this. And in fact, in this case, there is an algorithm that gives you exactly that. By the way, I will give it to you. Now, Chris actually showed that kind of problem, if you remember. So let me, you might want to do the following thing. What if, instead of doing the MMSE estimate, you will be doing the map estimate? That is, instead of doing equilibrium at temperature equal to square root of lambda, you will be looking to the ground state. In that case, you will be actually trying to look at the you will be looking at the magnetization on this line at 0 temperature. Okay? So first of all, this is a very, very hard problem to solve. Why? Because you see that you are always in this full replica symmetry breaking phase. Okay? And we didn't even mention replica symmetry breaking too much in the school, so it has to be hard. But you can do it. There is a full replica symmetry breaking solution of this problem. It's due to Giorgio Parisi. And if you send him a mail, he will send you the magnetization of the ground state, which he did. He sent me a mail, and he said, well, I'm sorry, I have only computed the magnetization up to 10⁻⁷. Is it good? All right, so it looks like this. Okay, this is the magnetization of the ground state. Oh, okay, by the way, I'm saying something wrong here. Ha, ha, ha. Sorry. The magnetization of the ground state is higher. There is something super subtle. So it feels like, haha, I have something better. No, because remember, what we wanted was not the magnetization, but the MMSE. Okay? Now, the MMSE at equilibrium is just 1 minus m. So it will do something like this. Okay? Now, it's tempting to think that the MMSE of the ground state is 1 minus this m. This is not true. Why? No, because I told you that the MMSE in general, the mean square error was something like Q0 plus Q minus 2m. It's only at equilibrium that it is equal to Q minus m. Okay? So if you look actually, if you compute actually the mean square error, you have something which is like this. Why? Well, I'm not even sure about this part, but forget it. But it's worst. Okay? So that looks that, you know, it's great to do this equilibrium stuff and all that. In fact, if you want to solve this problem, there is something very simple that gives you a very, very good algorithm. Just do spectral algorithm. Okay? If you take the spectrum of your J's, you take the leading eigenvalue, you compute the eigenvector, you take the sign of this eigenvector, and you will have something which is like this. Very close. Okay, so this is the ground state, and this one is spectral. So spectral methods are very good. And if you want to have something better than spectral method, you can use fancy stuff like semi-definite programming. Actually, Federico has an algorithm which goes very close to the optimal without any problem. Okay, so but what is interesting here is the following. We have a second order transition. And it seems that when you use stupid algorithm, I mean, not stupid, but just looking at eigenvalue decomposition, you have something good. All right. Oh, yes.
There's something really confusing. I don't. The x-axis of this plot.
Yes. The signal to noise ratio.
No. On the phase diagram, are you adding a uniform exchange, ferromagnetic exchange?
Yes, but you see, there is a gauge transform that I did. I rotate all my speed in the direction of the hidden assignment. So in that case, my model is really just random matrix plus a uniform uniform number, just a number. So it's really a particularity of the plus minus one model that you can transform, everything into random plus uniform.
So I mean, in reality, x is a random.
Yes. Okay, but if I do the analysis, if I'm the one doing the analysis, I might as well rotate the x to be all one everywhere, and that simplifies my life. In reality, it's ferromagnetic in the sense that if you project what you find onto X, then you have a positive overlap. Okay? Instead of doing this, I can just change variable and go into...
Okay, now what's the spin glass then?
The spin glass phase is basically here. Well, first of all,
I mean, in both phases, the axes are random, but in one case you can rotate away, and the other one you cannot.
I always rotate away, okay? The question is, what is the equilibrium Gibbs distribution doing? In this phase, it's doing a lot of stuff, but it's dominated by a configuration who have zero overlap with the hidden assignment. In the ferromagnetic phase, it's dominated by a configuration who have a positive overlap with the hidden assignment. By the way, we call this the planted assignment. These are called planted model. Okay? But if you don't want to think about it, think about, hey, I have hidden a ferromagnet here, can you find it? And this is really what we do. Okay? And if you want to think of, in terms of glass, it's kind of, hey, I have hidden a crystal phase in there, can you find it? Okay, speaking of glasses, what happens if you do this? Okay, you.
So in the spin glass phase,
Here.
lambda is not equal to lambda star.
No.
This is not the inference problem we are talking about. This
Well,
is
you could be
another
doing
problem.
inference. For instance, imagine I'm not giving you lambda star. I lied to you, and I told you, ha ha ha. You know, and I use lambda star equal 1/2, but I'm telling you, hey, you know what? I use lambda star equal to 10. So you will be doing your inference here with this lambda. So you will be in this place. Okay, so this is interesting. This is telling you that if you are doing wrong estimation, which is what we do in practice all the time, right? In practice, you never know the data are created. You might be in such phases. Okay? Even worse, even when I created the problem in an easy way, in which this is where I should be, if you are using lambda too large, you will be here in this mixed phase, which is ferromagnetic but spin glassy, which means that, you know, if you try to run a Monte Carlo algorithm, you have a lot of problems and everything. By the way, this is called a Gardner transition when you go from here to here. Never mind this. Yes?
Did you say that the Nishimori line is related to the Nishimori relation?
Yes, because on the Nishimori line, I have a problem which is exactly an inference problem. So on this line, I have all these relations that the expectation of f x1, x2 is equal to the expectation of f x star.
So that doesn't apply outside the line.
It's totally wrong outside the line, and this is the answer of what Laetitia asked yesterday. Okay? So by the way, all this thing of Nishimori and everything, it was discovered way before this connection with inference problem. Hidetoshi Nishimori was looking at this problem, and then he realized that there is a special line here in which you have a lot of crazy relations that are true, exact, rigorous, and he could derive a lot of stuff. Notice, by the way, that this line is always in a kind of simple phase. Here I'm paramagnetic, here I have ferromagnetic. All this spin glass hocus pocus is below. And this is one of the big truths of this problem. You are always in easy phases, either paramagnetic or ferromagnetic. Okay, this line is never crossing the spin glass phase. It's touching it here at the critical point. Okay, how does this change if you go to tensors? That means, how does this change if you go to the p-spin with a non-zero mean? Okay, if you go to the 3 spins model, you still have your Nishimori line here. Now this is how it looks. All right, paramagnetic, spin glass, 1 RSB, ferromagnet, and here you have a mixed phase. So it looks exactly the same, except it's 1 RSB. But these two lines here are first order transition line. In fact, there is a spinodal here, and here there is this thing called the dynamic transition that we spoke about before. Right? This was called the Kautzmann transition. This was called the dynamic transition. So you heard about this. Now what happens on the Nishimori line? So the good news is that what is happening on the Nishimori line is way simpler. Right? It's not looking like a dynamic or whatever. It's the first order transition. So let's look at what is happening here. So there are three colors now. 1, 2, and 3. Yes? All right, it's this is a glass transition. Okay, it's a rigorous, it's a exact glass transition. Okay, this one is first. Okay, let me call this a Kautzmann transition. Okay.
And one more remark.
Yes.
But here there should be also a Gardner thing down.
Yes, there is a Gardner down. Good point. I kind of do care. Okay, and here you have a full RSB phase. And here you also have a full RSB phase inside the mixed phase because it's mixed one RSB, but then it becomes mixed full. But I will not discuss this too much today. Okay, I want to look at my problem, which is on the Nishimori line. Everything is easy. The sky is blue, and the sky is without clouds, and everything is replica symmetric, and we can prove everything, which I was supposed to do today, but I won't. Okay, what is going on? So let's look at equilibrium. Okay. On this line, what is happening, if you look at the equilibrium magnetization, well, first it's 0. It is also 0 in this phase. And in the green phase, it jumps to a non-zero value. Okay? It's a first order transition. Now this means that here there is actually a Gibbs state, if you want, but its free energy is lower than the one is larger than the one of the paramagnetic. So at equilibrium, this is what you should find. It's just first order transition. Okay, there's really nothing mysterious. Good point. Now, if you start inside the paramagnetic phase, you always stay in the paramagnetic phase. So that means we think it's a really hard problem. Okay, I will change this in a few minutes, but you never do see hysteresis in this problem, yes. Okay? In fact, if you want to know what is happening if you do a simulation, and if you go in the blue line, you see a glass transition. Because I don't see the ferromagnetic transition, so I really feel like everything else is indistinguishable from a glass transition. But this is not what I want to discuss today. Let's stay in inference. Okay? So how can you understand this? So what you do? Okay. I will. Okay. So what I wanted to do today, but that you asked me all these questions, so we'll do it next time, is to compute the free energy of the problem at fixed magnetization. Okay? This is exactly what you will do if you would do a Landau theory of first order transition and second order transition. You would look with your order parameter what is the value of the free energy. Okay? So this is how it looks. In this phase, here, if you look at f of m, in the red phase, it's like this. Okay? So that means that the minimum of your free energy is given by F at m equals 0. If you go in the blue phase, all right, how does it look in the blue phase? In the blue phase, it looks like this. That means the equilibrium is still given by m equals 0. This is why you're a paramagnet. But there is something which is metastable. In fact, since we're in mean field, metastable is actually very stable. It's stable up to exponential time. And there is a good Gibbs phase here with a very good overlap with the truth. Okay, it's this one. It's just not the equilibrium. So if you sample things exactly, you never see it. Of course, if you start close to the equilibrium, this is where you are. How does it look in the green phase? In the green phase, and this is answering the question of Camille, I hope, this is how it looks. So now the equilibrium, now the free energy is minimized when m is positive. So thermodynamically, you really would like, if you could sample your posterior distribution, your Gibbs distribution, you will get something good. But the point is, since you start at m equals 0, you stay there forever. And this is what I meant. If you have pretty much any algorithm, like a Monte Carlo, or I will discuss tap equation and everything, you will stay here forever. Okay? And in fact, later on, this guy will have a glass transition. But never mind this. Okay? So that means that this problem is always hard from the point of view of algorithm. Now, if you change the problem just a little bit, and instead of having spins which are plus or minus 1 with 1/2 probability, you create spins which are plus 1 with probability rho, and minus 1 with probability 1 minus rho. Okay? And if rho is anything different from 1/2, there is another phase here, the orange phase, if you want, where suddenly your algorithm is working. Okay? Why? Because in the orange phase, f of m, function of m, now looks like this. Okay, that means that if you initialize close to m equals 0, you have no free energy barrier that blocks you, and you flow down here. So this is what we call the spinodal. Here it's the spinodal towards the ferromagnetic state, or if you want, in the problem of inference, it's the spinodal towards the hidden planted state. And if you think about this as a glass problem in which there is a crystal phase represented by the ferromagnet, this is the spinodal to the glass to the crystal state. Okay? Now, in terms of computational difficulty, what we have is, here the problem is impossible to solve. Okay? Even if you can sample the posterior distribution, you get something which has nothing to do with the hidden planted assignment. Okay? And you can show that, in fact, what you have created is undistinguishable, cannot be recognized. If I give you a planted, this one or a random one, you will not make the difference. Here, it's possible, but we think it's hard, right? And Chris mentioned all this. This is this hard phase. Okay, now, I'm sure that you are convinced this is hard, because I'm showing this diagram to you. You say, oh, yeah, sure, mean field transition and Landau and blah, blah, yeah, big deal. Okay, we are trying really hard to say some rigorous statement about this, because it's really a non-trivial statement from the point of view of computer science to say that something is hard. It's really hard to say that something is hard. I'm saying it's hard because Monte Carlo doesn't work, and I have other algorithm that doesn't work. In fact, as far as we know, there is nothing that works here. But it's maybe because we are not clever enough, right? So it's a hard statement. Yes, Zoe.
So if xi's are real, I mean, people use these tensor decompositions all the time with great success. And
good point.
That's real.
Good point. So if you use the tensor decomposition, like one of the things that people will do for tensors is to break the tensors and transform it into a vector. Okay? You can analyze what it does here, okay? And it works only for J0 scaling like a square root of n or something. So really huge. Now, that means that what you get in practice are much simpler problems than this one. But yes, it's a very good point. So it was analyzed. It was analyzed in this context by Montanari and Richard a few years ago at NIPS. And they showed that when you run AMP, you get the same kind of transition as you get from tensor unfolding methods. Okay, and now we have this phase here where suddenly you expect your Monte Carlo to work, and I will give you an algorithm that probably works. And this is the easy phase. Okay? So this is pretty much everything we have ever seen. I mean, I'm working in this problem since few years now with a lot of people in this room. We have variation on this, okay? And sometimes you have things a bit more complicated, and actually Lenka and Guillaume are trying to, and Federico are trying to do a zoology of all the kind of transition that you have, but pretty much this is the picture that we have basically all the time. Either we have a second order transition, and then things are nice. I mean, it's impossible, or it's easy. Or we have a first order transition, and then it's impossible, hard, and then easy. Now, if you think about what this is pretty much the physics of first order transition and of hidden metastable state. Think about nature of trying to solve a planted problem. Okay? For instance, the glass transition problem is nature trying to solve an inference problem where the ground state is the crystal. Now, at high temperature, nature is trying hard, and it's finding a liquid. So if you do high temperature, there is nothing you can do. You're in the impossible phase. Now, at low temperature, you know that you want to crystallize. So it should be possible to crystallize. But as we have discussed, we don't. We are in a supercooled state. Right? So think about the supercooled state as a hard phase. The equilibrium is actually given by the crystal, but we cannot find it. Now, maybe at low temperature enough, you have a spinodal towards the crystal state, and then things become easy again. And this is the easy phase. Right? So, this is liquid. That's kind of a solid, except this one is metastable. And anytime we are looking to that kind of problem with randomish, created problem in machine learning, we are ever finding one of these two pictures. Here, that was the case for the stochastic block model that Chris was discussing. If you do planted perceptron, which I probably will discuss, you also get that kind of picture. If you try to look at problems like colorings, right? Chris mentioned colorings and SAT. For instance, instead of doing SAT, you could be creating a SAT formula where you have hidden a SAT solution. You have the kind of picture. You can do the same with planted coloring, and you have, again, the same of picture. So it's pretty much what you find all the time. And the nice thing is that we can just understand those as first and second order transition. Yes? In this case, yes. Okay, but it can be very different. For instance, when I do community detection with 2 communities, I'm here. If I have more than 4 communities, I have that kind of stuff. If you are looking, I mean, it's 3 communities, I think it's always like this. Yes. And 4, it depends on the parameter. You can have both. Right? But that's pretty much everything what we find. Right? So I think it's very nice that all these can be mapped to first and second order transition of model that we already know. All right, so let me wrap it up and announce what I will do next time. So first of all, okay, two things. One, these are nice drawings, but this is a school, okay? So that means I need to tell you how to compute the stuff. How do you compute the stuff? Well, let's forget about everything out the Nishimori line. How do I compute things on the Nishimori line? Okay, for a start. Well, I need to compute the free energy, and from the free energy, I need to compute the average magnetization. Or even better, I would love to compute the free energy at fixed magnetization. How do I do this? I can do this with the replica method, or with the cavity method, but you will see cavity next week with Federico. And many of you have seen replica. It was discussed by Giulio Biroli, so you should be a bit aware of it. So since you didn't have enough of replica, I actually wrote the entire computation for this problem, the replica computation of this problem on the Nishimori line. As far as replica computation goes, it's one of the simplest. Let's say, I mean, the random energy model 1 is the simplest. This is really not hard, and it's on overleaf, and please do it. Okay, and you will get a nice formula. In fact, from memory, okay, what you will get, all right, you will get that the free energy of this problem for rank 1 matrix factorization. So the limit when n is going to infinity of f divided by n should be equal to the phi denoising with lambda m plus lambda m square divided by 4. So the free energy is extremely close to the denoising one. Actually, let me restate this. It is the minimum over m of this function, and the m equilibrium is indeed this, the one that minimizes this. So if you do replica, you can get this. Now you see why I insisted on this. It was not only pedagogical. I mean, I like one spins, but this problem looked like a one spin problem plus something. You get the function. This is f of m. You minimize it, you have an equilibrium magnetization. So it's a very good exercise. It takes a bit of time, so I will not be doing it. Instead, what I will do is something that will take me much less time. I will rigorously prove this. Okay, and I also want to do this because if you do this computation, you will see how crazy it is. Okay, you know, a lot of people have been doing replica computation since the last 20 years, and we get used to it. We know to do them. If you go to Rome for a few months, then you get a master in it. But you should not forget how crazy it is. You are doing some really, really crazy stuff when you are doing replica. Okay, so why do we believe it? It so happens that now we know to prove this thing. It's a bit of work, but at least for this problem on the Nishimori line, it's very easy, and I will show you how. Okay, it takes me less time than doing the replica. First thing. The second thing that I will do is to say, well, I was arguing that it was an easy phase. Like, yeah, sure, the free energy looks like this, so if I start here, I expect the dynamics to do this. This is true. You can actually analyze the dynamics, and that will be done by Laetitia Cugliandolo on very similar models. But I want to give you an algorithm even much simpler, but actually always work in the easy phase. And that will be an occasion for me to introduce you the tap equation, because this is what I will be using. Okay, and then if I have time, I will try to discuss further the connection between this problem and the glass transition. And if I have more time, I will try to discuss more involved problem in machine learning, such that perceptron, neural nets, compressed sensing, and everything, but don't count on it. Okay, and now I'm a bit over time, so I will stop here.